All right, these are the answers to the quick review here, chapter 6. First one wanted us to verify that y equal this satisfies this differential equation. So it's always good to kind of have, what are we working with? Here's the original function y. If I were to take the derivative, I'd have to do product rule, be 2x times e to the x as is, plus x squared times e to the x. The derivative of e to the x is e to the x. So this is our derivative here. So now when it asks for a derivative, I'll give it that. When it asks for the function, I'll give it that. So we have x times the derivative, 2x e to the x, plus x squared e to the x, minus 2 times the function, x squared e to the x, equals x cubed e to the x. All right? Now if we distribute this, I get 2x squared e to the x plus x cubed e to the x minus 2x squared e to the x equals x cubed e to the x. These cancel. And I've got what I want. So when we plug these things in, we know they're going to work. That's why they ask us to verify. They're not saying do they or don't they. We trust that they do. We just have to try to figure out how. So same thing here. I've got my y equals c e to the negative 2x. Y prime then would be c times the derivative of this. Derivative of e is just itself, so we keep that. And then times the derivative of the exponent, which is negative 2. So I'm going to put that negative 2 right there. Okay? So that's our function and the derivative. So I come over here, derivative negative 2, c e to the negative 2x, plus 2 times the original c e to the negative 2x equals 0. Boom, boom, they cancel out. And that's what we were looking for. All right, then they ask us to draw a slope field here with this differential equation. Now, you can go through point by point, plug them in. It takes a while, but you can get it done. That's not a problem. But what I'm going to do is just be a little bit clever here. I'm going to factor out that y. And the reason I'm going to do that is now when I look at this, this will equal 0 if y is 0 or if 1 plus x is 0. In other words, when y equals 0 or when x equals negative 1. And what that allows me to do now is to go to where y equals 0, which is right here on the x-axis, and make 0 marks, horizontal tangents there. And it lets me go to x equal negative 1 and do the same. And one of the things they'll grade you in the AP test for is, do you have the zeros correct? So if you're making a slope field on the AP test, right, you want to make sure that you have the 0 marks in the correct spots. Okay. Then after that, what they're interested in is, do you have positive slopes where they're supposed to be positive, negative where they're supposed to be negative? All right. So I look here, if y is greater than 0, and if x is greater than negative 1, then we're going to have a positive, right? So all of these should be positive right in here. But if x is less than negative 1 and y is greater than 0, then these are going to be negative. Or if x is greater than negative 1 but y is less than 0, then these should be negative. But if we're over here, if we're less than negative 1 and y is less than 0, then they're both negative, which means that these are going to be positive slopes in here. Now again, if you were to plug in your values, that's what you would see here, right? All these things would check out. You have all these positive slopes. You'd have all these negative slopes here. And again, if you just plug the points in, that's sure enough what you're going to find. Negative slopes here, positive slopes here. But again, the AP isn't necessarily interested in measuring this with a protractor and see if you got it right. They just want to know, do you have positives in the right spots? Do you have negatives in the right spots? So that's the big thing to key on there. All right, then we have this new idea, this Euler's method or Euler's method or Euler's method. I've heard it pronounced all sorts of different ways. I like Euler's method. I think that's a more German pronunciation, but whatever. All right, here's what we have to understand. Okay, we were given a point to kind of start with. That's the point 1, 2. So x is going to equal 1, y is going to equal 2. This is like a starting point. What we're going to do is we're going to jump to another point, then we're going to readjust and jump to another point until we get to where we want. What do we want to get to? 1.9. And we want to do that in 3 steps of 0.3, meaning we're going to go 0.3 up to 1.3, 0.3 up to 1.6, and then 0.3 up again to 1.9. So we're going to keep jumping by 0.3. That could be 0.25, that could be 0.2, could be 0.1, depends on what you're working with, what you were asked to do. This is what we were asked to do. And how you jump or what direction you jump is determined by this differential equation. This will give you a slope that you'll jump to, and then that'll give you your new point. Then you figure out the new slope, jump, and then keep doing that. All right. Each time we jump, we're going 0.3 on the x. That's our change in x. It's 0.3. Okay. Now, what we have to do is we have to figure out what the derivative, what is the slope at this point. We'll multiply it by that 0.3, which will tell us how much the y changed. And then we'll add that on to the y, and we'll do the same thing here. We'll just kind of keep going doing that process. So our derivative is 1 minus 2y. 1 minus 2 times 2 is a negative 3. If I do negative 3 times 0.3, I get a negative 0.9. That's how much the y changed in that jump. When we jumped from 1 to 1.3, our y came down negative 0.9. And so that brings it to a value of 1.1. Now what we do is we say, well, at this point, the slope is different. So let's figure out what the slope at this point is. So I'm going to put that in. 1.3 minus 2 times this is 1.3 minus 2.2. That's a negative 0.8. If I do negative 0.8 times 0.3, I get a negative 0.24. Bring that up, and we get a 0.86 then. All right. Well, I got one more time to do it. I'm going to use a calculator this time. So now I have 1.6 minus 2 times 0.86. That gives me a negative 0.12. Take that times 0.3, and we get a negative 0.036. Okay. 0.86 plus that gives us a final value of 0.824. That's our approximation. So using this derivative, this differential equation, and where we started, we think that at 1.9 would be roughly 0.824 in value. Okay. Now, obviously, if we use a smaller step to get there, we'll have a little more accurate approximation probably, but it would take us longer to do, right? So that's the, how difficult we want to make it versus how accurate do we want to make it. Sometimes we can't have both. We have to decide. All right. All right. And then the last one here is given this slope field here, we want to know which of these could be a solution to that. Now, when we say we're looking at solutions, we're looking at something that we could draw in here and get this shape. And you can see that our shape certainly looks something like this. It's going and then it kind of takes a turn, comes down. I'm following these lines, and then it turns again. And then it heads up, and then it heads up like this, right? So I've got something that looks kind of like this where I started. Now, I could have started this up here and did it, but I'm trying to get just a picture. That's what a solution might look like, all right? So then I look at the first option. The first option is quadratic, x squared. Well, I know that looks like a u, and that's not what I'm looking at here. I'm not doing that. Cosine, sort of, but it keeps going up and down, right? And this didn't go up and down and up and down. It actually starts to tail off here. So it's not going to be that, all right? Sine x, same thing. Sine x looks like that, not what we're looking at, okay? X cubed, now that's got potential, right? An x cubed graph kind of looks like that, and that's kind of what we're looking at. So I like that a lot. And then we have this e to the x plus e to the negative x, which, again, if you were on the AP and you got that and you're like, I have no idea what that looks like, well, then don't guess that one. You have a pretty good feel on this one. Go with that. And what you're going to find out is that that's your answer. This is going to have kind of more of a quadratic look if you were to graph it. You can do that later if you'd like. But go with the one that you feel a little more confident in.